When you navigate an unoptimized single-page application, you often experience jarring layout shifts and loading states. In a highly optimized Next.js application, the UI wires snap into a completed grid the moment the route changes. This speed is the result of managing a complex payload. A modern browser must handle dozens of concurrent resources: JavaScript bundles, CSS style sheets, custom fonts, and images, all within the same loading window. By default, the browser relies on a basic fetching heuristic. It parses the incoming HTML document from top to bottom, discovering and downloading assets chronologically as they appear in the code. This chronological parsing naturally creates bottlenecks. A large, non-essential JavaScript file discovered early in the document will block lighter, critical resources like typography or hero images from loading. This chart illustrates the critical rendering path. When assets load in this sequential staircase pattern, the browser cannot begin the final paint until the slowest resource finishes, delaying the render. Resolving this requires overriding default behavior, causing these blocks to shift left and load concurrently. We enforce this priority using 3 explicit HTML resource hints: Preconnect, Preload, and Prefetch. Achieving instant routing requires moving away from default browser heuristics to manually engineer the network waterfall using these explicit primitives. Preconnect is an explicit directive. It instructs the browser to establish early networking pipelines to a specific domain before an actual request is even made. The connection sequence begins with DNS resolution, mapping the domain name to an IP address. This is followed by the TCP handshake, establishing a reliable connection. Finally, negotiating TLS security completes the sequence, leaving an open pipeline ready for immediate data transfer. The primary targets for Preconnect are third-party domains. When relying on an external CDN, Google Fonts, or an API endpoint, the browser needs time to resolve those foreign origins. You can verify the time saved by these early connections using the timing tab within Chrome DevTools. This comparison shows the difference. The standard request on the left spends hundreds of milliseconds on DNS, TCP, and SSL negotiation. The pre-connected request on the right shows zero latency for those steps because the connection was already open. By setting up the pipeline before the browser's parser registers the need for the asset, Preconnect eliminates the connection penalty of third-party origins. Preload is an immediate execution directive. It forces the browser to assign a high network priority to a specific asset and fetch it immediately. This hint is strictly reserved for critical assets required to render the current page view, not for future navigation. The primary target for preloading is the largest contentful paint image. By tagging the hero image, it jumps to the top of the network queue. Custom fonts required for the initial viewport then join the LCP asset at the top of this fetching hierarchy. High priority means these assets command immediate bandwidth. Heavy preloaded assets, like large JavaScript chunks, can block the main rendering thread while they process. A common misconception is that assigning high priority to every resource makes the page load faster. This actually causes bandwidth saturation. When too many assets crowd the top of the queue, it forces essential HTML and CSS blocks to the right, delaying the final paint. To audit your fetching hierarchy, open the DevTools Network tab and enable the Priority column. You can isolate assets commanding immediate bandwidth by using the isPreload search filter. To find the fallout of over-optimization, look at the DevTools coverage tab. The red indicator bars in the coverage panel represent wasted bandwidth. JavaScript bytes aggressively downloaded at high priority, but never actually executed by the browser. While preload accelerates specific assets, its overuse starves the critical rendering path of bandwidth and slows the initial render. The third hint is prefetch. Unlike preload, prefetch is a low-priority, speculative hint. The browser will not execute a prefetch immediately. It waits until the main thread is free, executing the download during idle time. Its primary use case is preparing for future navigation, downloading the JavaScript bundles and API data required for the user's next likely route. Modern frameworks handle this differently. Next.js automates this speculative fetching when running in a production environment. Next.js tracks user behavior via the browser's Intersection Observer API, detecting when a navigation link crosses the bottom threshold of the viewport. When this intersection occurs, the framework triggers a background prefetch, downloading the necessary JavaScript bundle into a low-priority queue. This aggressive route fetching contrasts with Vite strategy, which focuses on optimizing the initial load of ES modules. Vite utilizes module preload, an explicit primitive designed for the eager evaluation of JavaScript modules. Rather than waiting for a module to execute to find its imports, Vite uses this hint to map and fetch the entire interconnecting dependency graph of JavaScript chunks at once. While Vite optimizes these chunks for the current page, it does not automatically fetch future user routes without manual configuration. Relying on automated fetching requires DevTools verification to ensure these background requests are actually executing as expected. Idle time fetching is usually too fast to see. You must simulate a slow 3G network environment in DevTools to make the background activity visible. With throttling enabled, scroll down the page to force a navigation link into the viewport, triggering the intersection observer. In the Network tab, you can locate the dynamically appearing JavaScript file. It should register a low priority status, and the initiator column will explicitly list Prefetch as the origin of the request. Automated route fetching is a form of proactive speculation. Relying on it without verifying idle time execution in DevTools can obscure silent network bottlenecks. Using explicit resource hints shifts the burden of performance from the browser's generalized heuristics to the developer's architectural control. A verified optimization strategy requires a strict three-step hierarchy. First, Preconnect resolves external origins early, securing the pipeline. Second, Preload grabs critical fonts and LCP images quickly without starving the rendering path. Finally, Prefetch pulls background bundles during idle time, preparing future routes without interrupting the current view. Automation from tools like Next.js and Vite is powerful, but it must be audited using the DevTools priority column, the Is Preload filter, and the Coverage tab. Optimizing the network waterfall requires a transition from accepting default browser heuristics to enforcing architectural control, then proving that control against the browser's raw telemetry.